Welcome to another video by Quiet Mind, Happy Heart. This video is intended to help you relax, especially before bedtime. Now get comfortable and let's get started with the lecture. Tonight we're going to talk about sets of points. I'm hoping that you won't find this a terribly boring lecture. Some people even find math to be exciting. Let's move on now to talk about sets of points. Lines, curves, shapes, and even solids can all be classified as sets of points. In math, a point is understood to have no specific or set size. It merely marks a position. Between any 2 points, there can always be another point. The sets of points form lines, curves, circles, and other shapes, all of which consist, therefore, of infinite sets. Consider a figure in which we have an equilateral triangle bisected through its primary vertex with a line that we can call line L. This line could be described as the set of all points which are the same distance from the other 2 points, which we will call points A and B. Any point on L is the same distance from A as it is from B. In other words, it has the property that A is equal to B with mathematical symbols being used in the usual way. The line through our equilateral triangle is therefore called a perpendicular bisector or mediator of the length. It cuts the triangle into equal lengths. So therefore, L is the set of all points of P such that the relationship of A to P is equivalent of the relation to A to B. Consider also the description of a surface as a set of points. Forgive me a moment while I have a small drink of water. Moving on to our description of sets of points. Consider, for example, a circle with a radius of 1. The circle is the set of all points which are 1 centimeter from C, being the center of the circle. Such a surface is called an open disk. Intersections are the point where two lines meet. Let's consider L and M, the parallel lines. Now, I was mentioning that I hope you don't find this lecture too boring. But please bear with me now as I talk about the points of intersection. The line meets the curve at 3 points, and the points are common to the sets on the line and the circle. This is called an intersection. Let's move on to another example. Here we have a Venn diagram showing the line T, which divides a plane into 3 separate sets of points. Those on the left are nearer than those on the right. A curve also includes sets of points, and this curve, of course, can pass through 2 parallel lines, which also contain infinite sets of possible points. Lines on a plane can also be distinguished from one another in a similar way. Parallel lines are given the name of the form x equals a number when there is a 1-to-1 correspondence between numbers and lines. A heavy line which forms x equals 0 can be called the up axis, and the distance from which on the scale shown is given the name L. Now we have some lines which go across the page, and we want to give them names as well, and we will call the lines Y lines in the form of y equals a number. As a marker for these lines, we shall also use the other line, which is y equals 0, and we will call it the across axis, and a scale for convenience will be the same as for the x line and will be marked on a line running up, as we can see here. Notice the scale for the line which is written is on the across axis where y equals 0. In the same way, the scale for the y is written on the up axis where x equals 0, and this can also be called the y-axis. The pattern of lines up the page called x and across the page called y can be used to name sets of points. For example, the point A is the intersection of the line where x equals 1 and y equals 2, and it is therefore called the point 1, 2, and the intersection of the line x equals 2 and y equals 2 is the point at which B equals the point 2, 4. The intersection of x and y where x is 0 and y is 0 is called the origin, because it is the point on both axes where we begin to measure the lines, and we can name other points on the line C, D, E, and so forth. Every point on the page can be represented as an intersection of one line where x is present and one line where y is present. For instance, point 2, 3 is the intersection of the line x equals 2 and y equals 3. Coordinates of this type are called Cartesian coordinates, after the French mathematician called Descartes. Descartes was also a writer, and he invented this form of mathematics. The study of geometry by means of Cartesian coordinates is of great importance in math and also in physics, for example, in determining how high and how far a rocket can travel into space. Now, let's look at a practical problem. Using a squared paper and a scale of a half-inch to a unit, draw a line across of 8 units and a line up of 12 units, and plot the points A, which is equal to 2, 2, B, which is equal to 4, 5, C, which is equal to 8, 8, D, which is equal to 10, 7, and E, which is equal to 12, 5. Now join the points. Does any shape emerge? Draw lines where x equals 5 and y equals 4. Now write down coordinates of any points of intersection across the lines which you have drawn. Now refer to the figure on this page where we see the parallel lines in which we have the coordinates of points x, y, and z. Do you notice anything about the coordinate of any other points on these lines? Could any point lie on a line which we could call M, which is extended indefinitely both ways? Now, as we know, our knowledge of Cartesian geometry has helped us to draw lines parallel to axes and points on a plane to be named. For example, point 3, 5 is the intersection of x equals 3 and y equals 5. It can therefore be seen that the name of a line, or more accurately, an equation, expresses properties associated with the coordinates of every point on that line. Moving on to the next example, we shall now plot a line, and we will draw a line whose equation is known to us. For example, the equation of a line y is equal to 1/2 of x plus 1. Every x line meets this line at a particular point. We shall find 3 such points, and these points will enable us to draw the line by means of a ruler, where line x equals 4 meets it at a point whose x-coordinate is 4. Otherwise, this point could not belong to x equals 4. The equation of the line y is equal to 1/2 plus x tells us that the x-coordinate equals 1 more than half of the y-coordinate, so that if the x-coordinate is 4, the y-coordinate is 3, and similarly the line x equals 1 meets the line at the point where y is equal to 1.5, that is, at the point 1, 1.5, and the line x equals 3 meets it at the point 3, 2.5, and 3 points can then be plotted and joined with a ruler, and we can write the equation beside it. In the previous part, we found that a line represented 1/2 x plus 1 equals y, and now we move on to the points of a line where y equals 2x plus 1, and plotting these points, we consider the line that can be drawn. And now we consider the line y is equal to negative 1/2 x plus 3. It meets the x-axis where y equals 3 at the point 0, 3, and the line meets x equals 1 where y equals 3 minus 1/2, that is, at the point 1, 2.5, and it meets x equals 2 where y equals 3 minus 1/2, and the line can be joined by forming these points. Now compare the coordinates of those points and copy and complete the graph. Now, this becomes more complex when we have a view of what we can call the double cone. It consists of two identical hollow circular cones, one resting directly on top of the other at one of their vertices, and a dotted line can represent the side view of the planes cutting the double cone in various ways. We can draw diagrams to show the shape of the previous lines and the previous examples. Now, for your homework, I would like you to take some cardboard, not too thick, perhaps less than 1/8 of an inch, and now take a thick marker and draw out a circle with a radius of 3 inches and cut it out. Now, from any point on the edge of this circle, draw a line which passes through the center of the circle. Now, as we know, such a line is called the diameter. Cut along this line and bend the cardboard into semicircular discs, and bend these further to form a cone. And we can then join them using tape or some sort of strong glue, and we can fill these then with something like Play-Doh or putty and allow them to harden overnight. We can also use a nail to join the two cones together. This will be an important visual aid for you as we go forward.